Okay, so we want to derive the probability density function for a general bivariate normal distribution. And the way we're going to do this is kind of like the way we usually derive the distribution function for a general single variable, the univariate case of normal distribution. In the case of a single variable, parameters mu and sigma squared, you can actually do a linear transformation of a standard normal distribution using x equals z sigma plus mu. Now, but what we want to do actually, the way I'm going to do this is I'm going to use the joint cumulative distribution function and then differentiate it to get the joint PDF of a bivariate, general bivariate normal distribution. But we will also make transformation something similar to what you see in here. Okay, now in the case of the bivariate, so let me just write some things here. In the case of a bivariate normal, the bivariate normal distribution has 5 parameters. Okay, these parameters are the mean of each of the variables. Okay, and then we have the variances of each of those. That's 4, and we also have a correlation between them. That's correlation between x and y. Between x and y. Okay, now this correlation number is going to be between -1 and 1, correlation coefficient. Okay, now here's how we're going to actually proceed in this case. What we want to do is we're going to introduce 2 variables, z1, z2. Okay, these are independent. Suppose these are independent, standard normal. Random variables. Okay, so we're going to start with those 2, and then we're going to make the transformation. We're going to let x be sigma x z1 plus mu x, which is similar to the univariate case. The distribution of x here follows normal with the mean mu and variance sigma squared, right? Just like the ordinary normal distribution. Then we're going to introduce a second variable y. This one is a bit more exotic. It's going to be sigma y and then rho z1 actually plus sigma y times 1 minus rho squared and then by z2 plus mu of y. Okay, so we're going to introduce these 2 variables. Now in this expression, if we solve for z2, let me do that because we're going to need that later on. If you isolate z2, z2 turns out to be y minus mu y negative sigma y rho z1 all over sigma y square root of 1 minus rho squared. Okay, that's what z2 turns out to be. So now we can actually move to find a joint cumulative distribution function of xy, and then again from that we'll be able to come up with the joint density function. Now the joint cumulative distribution function fxy of xy, actually let me change that to, I'm going to go st here. Okay, it will make it a little easier. So that's, by definition, that's probability of x less than or equal s and probability of y less than or equal to t. Okay, that's just definition of joint probability distribution. Now remember what x was, right? Our transformation, which was sigma x z1 plus mu x, that's less than or equal s, and y was the more exotic one. It's right up here, so I'm going to use that, which is sigma y rho z1 plus sigma y square root 1 minus rho squared z2 plus mu y. less than or equal to t. Again, definition of joint distribution. Now, for the first inequality, I'm going to solve for z1. Now, because I'm going to subtract mu from both sides, divide by sigma, and because sigma is positive, we don't need to change the direction or sense of inequality. So that's going to be z1 is less than or equal to s minus mu x divided by sigma x. And then for the second part, we're going to solve for z2. And remember, I solved for z2. This was z2. And of course, we have a t on the right side. So I'm going to write that first. Therefore, z2 is going to be lesser than or equal to t minus the expression that I had up here. This one. Minus mu I negative sigma y rho z1. All of that divided by sigma y square root of 1 minus rho squared. Okay. Again, that's the definition of joint cumulative distribution function. Now we're going to actually write these. Therefore, f of xy is going to be now 1 over 2 pi, the integral from negative infinity to s minus mu x over sigma x e to negative z1 squared divided by 2 times the integral from negative infinity to t minus mu y negative sigma y rho z1 divided by sigma y squared of 1 minus rho squared. Okay, times, or actually that's just the upper limit of integration, and then times, or the integrand, not times, but the integrand would be e to negative z2 squared over 2. This is going to be dz2, and then the outside differential of z1. Perfect. And there we have it. So next, I'm going to do the following. I'm going to bring, this is going to be 1 over 2 pi sigma y square root 1 minus rho squared. Okay, this part. That's independent of, with respect to the variable z1, that's a constant. So I brought it outside the integral. And then the integrand becomes negative infinity to infinity of s minus mu x over sigma x. And this is going to be e to negative z1 squared over 2 times. And next, we're going to have integral from negative infinity to t of e to negative 1/2. And then we're going to have y minus mu y negative sigma y rho z1 sigma squared y 1 minus rho squared. And the numerator is going to be squared. Okay, and that's going to be dy. So what I did is I changed the variables. Instead of dz2, I went to dy. Notice the limit of integration, let me show you here, is t. It used to be that. And the integrand used to be z squared, so I replaced z sub 2 squared. So I replaced z sub 2 squared with that, all of that. So that's how we got to the next step. Okay, now what we need to do next is, this is kind of a little messy here, confusing. I'm just going to go ahead and write this as, I still have the fraction in the front, right? 1 over 2 pi. And this time I'm going to bring sigma x also, sigma y squared to 1 minus rho squared. and I'll show you where that's coming from. That's negative infinity 2. I'm going to do the same thing that I did with the upper limit here. We're going to change the variables, right, from z1 to x. So that's going to be negative infinity to s, and then negative infinity to t. Now remember, z1 was right up here. Oh, I didn't solve for it here. If you do, z1 is going to be x minus mu x over sigma x. So that's what I'm using down here, right? And here, instead of z1, I'm going to use that fraction. So this is going to be negative 1/2. It's going to be e to negative 1/2, and then parentheses. I'll show you how I'm getting this in just a moment. X minus mu x over sigma x quantity squared plus y minus mu y negative sigma y rho, and then z1, which is x minus mu x over sigma x quantity squared, right? In the numerator, the whole thing. Hold on. I already. Okay. Yeah, I'm working on this part. So that's gonna be the whole thing squared, and then divided by sigma squared y 1 minus rho squared. Okay. And then we have dy and now dx. Okay, that looks good. Now let me explain where these are coming from. Okay, I had sigma y here and then sigma x down here and then the 1 minus rho squared. Where do these come from, right? It goes back because we are actually changing variables here, right? So let me write this one again. Z1 was x minus mu x over sigma x, right? So if you take the derivative of both sides with respect to x, this is going to be, and this is like 1 over sigma x times x minus mu x, right? So it's going to be 1 over sigma x, and derivative of x is just dx. Okay, so that's 1 over sigma x dx. That's where this sigma x came from when I switch from dz1 to dx. Okay. Now, let me show you where this expression came. Right, that's when we switched from dz2 to dy. So let's work with that one. Okay, now my z2 was actually, I'm going to write it in 2 fractions. It's easier to look at the derivative next. Sigma y square root 1 minus rho squared plus negative mu y negative sigma y rho z1 over sigma y square root 1 minus rho squared. Okay, so that's what z2 was. And what I did, this is z2, and I split it into a y over that, okay, and then this fraction. And the reason I split it is because I'm about to take the derivative with respect to y. So all of these are constants, right, with respect to y. Therefore, the derivative of that would be 0. So that's why I split it the way I did. See, the derivative with respect to y here would be 0 because there is no variable y there. Now, if I take dz2, the derivative is going to be 1 over sigma y root 1 minus rho squared, and then dy1 there. So when you take the derivative, this part is 0, and this acts as a constant multiple of y. So if you look at now this fraction, that's exactly what I have up here. That's where that came from. Okay, so let's see, that looks good. Now the next thing that I need to do is let's see. So I wrote it. Boy, this integrand is a bit messy, isn't it? I'm okay with the fraction in front. The limits of integration look fine. Okay, now what I need to do is I need to work with this exponent right here, that exponent. So let's focus on that. We're gonna work with that exponent. Okay, and in fact, let me look at the entire exponent so we don't have to do it in 2 steps. Let me look at the entire exponent. So that entire exponent is now going to be I'm gonna have negative 1/2 bracket is x minus mu x over sigma x quantity squared, right, plus, and then I have the second part, this part. Now I have written that on a piece of paper for myself, so this way I can move my screen up a little bit. Okay, that part of it is going to be y minus mu y, and then negative sigma y rho x minus mu x over sigma x quantity squared. Okay, divided by sigma squared y 1 minus rho squared. All right, and this is negative 1/2 x minus mu x over sigma x quantity squared. Didn't do anything with the first fraction. Now the second fraction, I'm actually going to square the binomial. Okay, I'm looking at that binomial and I'm going to square it. So I get the first term squared. This is going to be plus, I'm going to have a long fraction because I'm expanding the binomial. So I'm going to have y minus mu y squared plus the second term squared is going to be sigma squared y rho squared, and then x minus mu x over sigma x quantity squared, negative twice first by second, mu, or actually y minus mu y times x minus mu x, and of course there is a rho and a sigma y there right in here. I just move them back there to the end. All right, and then the denominator of course is sigma squared y 1 minus rho squared. There. All right, so what I want to do next is I'm going to factor 1 minus rho squared, okay, from inside the bracket. So it's going to be negative 1/2 1 minus rho squared. Okay, now the first fraction, because this part it doesn't have 1 minus rho squared, so we can multiply top bottom by 1 minus rho squared, and that's going to create a 1 minus rho squared. See, so I can cross them out like that. That's how I can create them. And then times x minus mu x divided by sigma x quantity squared plus with this long fraction, I'm going to break up the numerator into 3 parts. The first part is going to be y minus mu y over sigma y quantity squared. Remember, the 1 minus rho squared is factored out, so it's no longer there. So it's just sigma squared y. I'm going to divide each of these terms in the numerator by sigma squared y. And then plus, that's next one, the sigma squared y here for the second fraction, they're going to cancel out. So I'm just going to have rho squared times x minus mu x over sigma x quantity squared, negative 2 rho x minus mu x, y minus mu y, and divided by sigma x and sigma y. Okay. Sorry about this. This is acting up again. Let me hold on. Okay, so there's this bracket. All right. Now what we can do next, if you distribute a rho squared to this fraction and a rho squared to that fraction, we get the same things, right? One is positive, one is negative, so that creates opposites. In other words, these cross out. Okay, but remember, we need to distribute 1 times the fraction still. But those terms will vanish. And then what we have next step is negative 1 over 2, 1 minus rho squared. And then that's just going to be a single term, x minus mu x over sigma x quantity squared. Okay, plus the next term is going to be y minus mu y over sigma y squared, negative 2 times rho parentheses x minus mu x, y minus mu y, all of that divided by sigma x, sigma y. And there we have that. So all I've done, again, this is the exponent. All of that is the exponent in the integrand in my exponential form. Let me go back up here. Remember, that's what this was. So we managed to work those off. Now, my next step, I'm gonna rewrite my density cumulative distribution function f x y using this new exponent. So fxy is going to be the integral from negative infinity to s, negative infinity to t. I'm going to move the fraction that was in front, 1 over 2 pi sigma x sigma y square root of 1 minus rho squared. Okay, and then e to the power of, instead of e, let me just write exp. So when we go exp, for example, w, that means e to w. Okay, so that's what I'm doing, instead of rewriting the expression using the exponential format. So it's going to be e to the power of everything that you see here. So this is going to be negative 1/2 times bracket x minus mu x over sigma x squared plus y minus mu y over sigma y. Boy, this is messy, isn't it? Negative 2 times rho and then x minus mu x, y minus mu y. Oh, here I'm in the corner again, that's why. Y minus mu y divided by sigma x, sigma y, and then dy dx. Okay, and what I did again was I brought this out to the front. Okay. No, actually, I'm sorry. This was something different. Hold on. This is different. Okay, I need to bring right in here. I need to adjust this part. Hold on. This is going to be -1 over 2 times 1 minus rho squared. Sorry about that little piece. Let me erase this and rewrite it for you. Hold up. Okay, that looks better now. So I just managed to fit the whole thing in there. And again, what I needed to do is I needed to bring that in front, which I did right in here. Okay. The reason these came about, remember, is when we changed the variables from z's, z1, z2 to x and y. Okay, so this is what we actually wanted to accomplish. We wanted to find the joint cumulative distribution function. So this is the joint cumulative distribution function. Now we can take the partial derivative of this one, but we can also at this point recognize that this is the form of the density. And there you go. This is the joint density f xy of a bivariate normal distribution. Now if rho is 0, by the way, here, if the correlation is 0, then the joint density turns out to be product of the marginals. Okay, which in this case it shows if rho is 0 means the two variables are uncorrelated, then the two will also be independent. This isn't the case of normal distribution only. If rho is 0, then uncorrelatedness implies independence. But that's what we wanted to do. So hopefully you can follow all the steps. It's mostly algebraic steps, and of course some integration, but we did not really integrate anything. We just established the integrand here. Okay, and hopefully this is going to help you out.